Hello, I'm David. I'm the coordinator of the Maths Learning Centre here at the Uni of Adelaide. It's semester 2, 2024, and this is the revision seminar for Maths 1A. And I've had some requests, and we are starting with subspace, span, basis, etc. That stuff. Before I continue, this is your revision seminar. You're allowed to interrupt me. If I make a mistake, like putting a minus where there should have been a plus and vice versa, or 1 + 1 = 1, or any of those things, tell me immediately. Interrupt me, okay? Just don't wait. Tell me straight away. Any other question, maybe wait to the end of a sentence, but otherwise feel free to interrupt. Those of you who are on Zoom, you can either turn on your mic or you can put something in the chat. And I charge everyone in the room to keep an eye on the chat for me. And if something new appears, can you let me know if I haven't noticed yet? I will try my best to notice. And I will also try my best to stop talking at least once every 10 minutes to give you a chance to process and ask questions anyway. Okay, there you go. As I said before, we started recording. This whole span, subspace, basis thing is taught in a weird direction for a start, but is also the most different thing to any other maths you've probably seen before. It's not really like anything else. And so it can take a while to get a handle on what any of it means, and also how to do it. You don't have just like a vibe where you can go, okay, I get how this area of maths works. Because most people have an idea of how calculus generally feels, but you don't have a feeling for this other than just, so that's okay to feel that way. I'm going to work through that feeling, and we're going to try and help you feel better about it. So, the first thing I want to say is about what vectors are. To a mathematician, to a physicist, a vector is a thing that has, what does the character in Despicable Me say? Magnitude and direction. Okay. Yeah, nice physics maths joke there. It was a good one. Magnitude and direction, but for a mathematician, that is not at all anything about what a vector is. A vector to a mathematician, well, there are no just single vectors. A collection of vectors is a collection of things that you can do addition and scale and multiplication on. In a reasonable way, okay? So, addition works in the order, you can add in whatever order you want and get the same answer, and you can multiply several numbers one after the other, and it doesn't matter what order you do that, and then you get the same answer, and multiplication expands out over addition, and all those things. That's what vectors are to a mathematician. Cool. And the reason I say that is because one of the reasons that you learn things about span, subspace, basis in first year is because in various second and third year maths in various degrees, they borrow ideas from this to apply to things that you didn't think were vectors before. So I'm just warning you, it'll happen. So you have to allow yourself to think of other things as vectors later. But for now, most of the things that we think are vectors, at least in this course, are things with coordinates. Something with 4 coordinates like that is a vector in R4. So for this course, vectors are pretty much just things with a list of coordinates. And the R is referring to the numbers that we are allowed to choose to put in these coordinates, and the 4 is referring to how many coordinates there are. Doing okay? All right. And so at its deep heart, that is all a vector is to a mathematician, just a list of coordinates, which is why we're happy to have things with 400 coordinates, because we don't have to imagine what they are. They're just things with coordinates, and that's okay. But we borrow from our understanding of R2 and R3. And R3 has 3 axes, usually X, Y, and Z. This is the point X, Y. This here is a point X, Y, and Z. That's R3. And we just imagine everything as if it was a point in space. And that's a really important thing to note, that to a mathematician, when you're just thinking about one set of coordinates sitting there all by itself, it's a point. But if we're going to start adding them and multiplying them by scalars, we have to think of them as arrows. I can't use the cross for times because that means something special. So that's really important. And you get to decide how you look at a vector at any moment to decide what you think it is today. It doesn't matter. It's a little bit like a fraction is capable of both being a comparison between two different sizes and a place on the number line. It can be both, and so can vectors too. Vectors can be points, so they can also be journeys between points, and you get to decide what you want to do with them. Okay, just hold that in your mind. Keep it close, because that is how we have to think about what subspaces are, with both of those things simultaneously. Subspaces are sets of points, but you tell whether something is a subspace by the way that addition and multiplication work. So now I'm up to doing that. But I'm nearly there, nearly there. Span is both an object and an action in maths. So you know how I said that vectors are things that you can do addition and scalar multiplication to? Well, that's what spanning is, doing addition and scalar multiplication at the same time. So if I have just some vectors, that is a set with 2 vectors in it. This is just 2 dots. Oh, my 3D diagram is kind of stuck. But let's see, 1, 2, 0, and 0, 1, 5. At the moment, this set just has these 2 dots in it, and that's all. I'm just thinking about it, so it's this dot and that dot. Doesn't contain anything else. This is a set that's defined by listing things at the moment. There are 3 ways to define a set, and at the moment I've defined it by listing what's in it. But when you do that being vectors, it is possible for me to add them together. And it's possible for me to multiply them by scalars, and it's possible for me to multiply them by scalars and then add them together. And any combination of addition and scalar multiplication I can do to these vectors. Technically, I can do it to other vectors, but I'm imagining just starting with these ingredients and seeing what can I make from those. So when I do this, putting a span in front of this is doing the action of finding all possible combinations of these 2 vectors and coloring them all in as dots. So 0 of 1, 2, 0 plus 0 of 0, 1, 5 is 0, 0, 0. So I'll color that one in. That's this dot here. It's going to be in green. And 1 of 1, 2, 0, and minus 2 of 0, 1, 5 would be 1 minus 2 times 0 is still 1. 2 minus 2 times 1 is 0. 0 minus 2 times 5 is minus 10. That was a bad move. That's like down here somewhere, right? Off the page. Yeah, it's approximately here, right? 1, 0, down there. And I can do that to lots and lots of points. And as I color them in, I will make an object. And I can choose whatever numbers I want to put in any of these places. Something times this and something times this equals some vector with coordinates. And that is what span is. It is the collection of all of these things as points that you color in. That's how I imagine it anyway. So this thing is the set of A1, 2, 0 plus B0, 1, 5, such that A and B are all the numbers in the real numbers. That is the formal definition of what span means. If you like, it's all linear combinations. And I didn't say what that word was. That's what this thing is called, a linear combination. Okay. So the span, that's what this object is. The span is what you get when you color in all those points. And for these points here, I'm just going to need some vectors in space. Bear with me. That's going to be my x-axis. That's going to be my y-axis. And I'm going to have my z-axis pointing upwards. You can do it, Texter. Nope, maybe the pink one. Like that. X-axis, y-axis, z-axis pointing up. And I had the point 1, 2, 0, which was here. And I had the point 0, 1, 5, which was about there in space at the end of my pencil. And I'm going to put my finger there, and I can have any multiple of this vector, because I can have something times this vector and 0 times the other one, and that will produce all of these points. And I can have any multiple of this vector, which will produce all of these. And I can have any combination of something on this line and something on this line, which will fill in that plane. So this is where the other line was originally, and I can fill in all of that. But I can't make anything over here. I can't make anything over here. I can make a heap of stuff under the table as the plane goes through if I use my negative numbers. But I definitely can only make things on that plane. And that is how spanning works. If you have a single vector and you do the span of that vector, what you will make is a line. If you have two vectors and you make the span of those vectors, what you will make is a plane. Now, let me just, they don't have to be the same length. So I was making something like that, and I can make the plane that goes through both of those arrows. I started out with them just being points, which is my pencil tips, but in order to think about what they make, it's easier to think of them as arrows. If I had these two vectors, I would still only make a line because they're already in a line. If I do combinations of these two, I can just only make more of the same things. So you need your two vectors to be pointing in different directions in order to span a plane. And you wouldn't have noticed, but I just used the word span as a verb as opposed to as a noun. So the span of these two vectors is this object, the plane that I make by coloring in all the linear combinations. But the act of making that plane is called spanning. There are no English words I've been able to think of that are both the name of the action and the name of the thing you produce by that action. So there you go. Unfortunately, that's the way it is. We have some things that are close, like produce is the verb and product, which are very close together as words, is the noun, but we don't have anything like that. That's the way it is. Sorry, guys. You don't cake a cake. So anyway, I've been trying for decades to try and think of something that does that, but I haven't got there yet. Anyway, how are we feeling about that? Okay. Do you have any thoughts that you would like to share at this time? Yes. That's a great question, and I love the way you ask it. What do you do with this knowledge? Okay, we will get there. Okay, but thank you. I will try and hold that in place. If I don't answer it sufficiently, please ask again. Okay. But just stepping back, if vectors are things that do addition and scalar multiplication, it seems reasonable we would really care about what you can make with scalar multiplication and addition. And so if we've got some vectors, we can say, well, what can we make from the operations that vectors do out of these vectors? And in general, you can make planes. If you have three vectors that are pointing different directions, you can make the entire 3D space. If you happen to be living in four-dimensional space and you had three vectors, you couldn't make all of four-dimensional space. You'd need four vectors to do that. So when you start thinking about being able to make certain shapes from the vectors we've got, that's also the idea of spanning. So can I find, if I'm thinking of a plane, can I find some vectors that span that plane? And that is a good question. And so one of the reasons you might want to do that is kind of a physics sort of reason. In physics, it can really help to put your coordinate axes in the right spot to make your problems easier to solve. It works in engineering, works in physics, even in other flavors of science that aren't so deeply mathematical as physics. It helps to choose your time equals 0 at the right spot. So if you choose your coordinate axes in just the right way, then it can make your problem easier. And one of the things that this spanning thing does is choose a pair of coordinate axes, because you write everything else in terms of how far you are along these two lines. Because 1 along this line would be 1 times this vector, 2 along this line would be 2 times this vector. So you write everything in terms of how far along those two lines you are, and that's what coordinate axes do. And so the act of spanning, in some senses, is setting up a pair of coordinate axes. They may not be very good ones, because they might not be at right angles to each other, and that's a bit hard. And this length might be different to this length, and so that's a bit hard. But still, it's a thing you can do. So there are better things to choose to span with, and you'll get to that in Maths 1B. So foreshadowing, it's happening at some point. Okay, that's spanning. And I have gotten very close to talking about what subspaces are, because what spanning does, the act of spanning, and you get color in all those points, the object that you make is a subspace. So that's useful to say. It's not the definition of subspace, but it's useful to know that whenever you span some vectors, the object you make is a subspace. I'm just going to say, when you create the span, when you create the span of some vectors, you are making a subspace. So if you want to have an idea in your head of what a subspace is, it's useful to think of it as a span of something. And since you know that when you span things, you make lines and planes and that sort of thing, then that is the physical picture of what a subspace is to you. It looks like a line or a plane or a three-dimensional object or something like that. They tend to be flat or straight. Curved things are not subspaces because you can't make them by spanning vectors. And it is useful to know that it is true that all subspaces are the span of something. I'm going to repeat that again in a minute. Okay, So the reason I'm talking about this in multiple different directions is it's the only way that you can come to feel that you understand it. The sensation of understanding only happens when there are ideas are connected in your brain. A new idea that's just sitting all there on its own, no, I am on this video as well, all there on its own, not connected to anything, you never feel like you understand that. Only when it's connected to other things do you feel like you understand it. So I'm trying to connect the idea of subspace to the idea of span and to the idea of geometry and space and all of those things to make it easier to feel like you understand. Okay. And you may be wondering, if all subspaces are the span of something, and when you span, you make subspaces, why do we even have the word subspace? Why don't we just call them spans? This is a reasonable question. I would prefer a world where we only had one word for this, but I'm sorry, that's not the world we live in. Because the idea of subspace was created independently of the idea of span. Only later did we discover and prove that all spans are subspace, all subspaces are spans. So, sorry, that's just the way it is. And actually, if I want to be really, really anal about it, there are some very fancy, crazy vector spaces where not all the subspaces are spans. Don't get me started. But we're not living in those lands. We're okay with those. R, whatever, all subspaces are spans. It's okay. So, okay. So what is a subspace? Well, it's useful to know that the prefix sub means under or inside. Something like suburb. Urb means city, as in urban. Sub means inside. A suburb is a city inside another city. That's what a suburb is. And so a subspace is a space inside another space. And so if we think about R3 as being space, then a plane inside that is a smaller space inside the bigger space. That's what the idea of subspace is. And mathematicians are very interested in sub-things. They'll define a thing they call a field, and they'll say, aha, let's make a subfield. And they'll have a group, let's make a subgroup. They'll have sets, we'll make a subset. They like things inside bigger things. It appeals to them. And so what a space is a collection of all the vectors that you can do addition and scalar multiplication in a reasonable way. That's what a space is. So I'm just going to add this. This is like a vector space. And so what a subspace is a collection of vectors inside a bigger space where you can do addition and scalar multiplication in a reasonable way just using those vectors. What it means is it's self-contained. So a subspace, the idea of subspace that is self-contained with plus and scalar multiplication. The idea is that if I made that plane and I removed all the rest of the points in 3D space, I could still do addition and scalar multiplication perfectly reasonable with just the points in that plane, because I can only make points in that plane, so it doesn't really matter what all the other points are. That's what it is. So this is what we think it is. And then we create a definition that matches with that thought. It has to be self-contained, which means that you have to be able to do addition and not escape. You have to be able to do scalar multiplication and not escape. And it has to have some vectors in it at all, because that would be stupid. But also, all subspaces have a zero vector, and so we need it to have the zero vector. And so the definition is that the zero vector, now I need to write it properly. A set always called W for some reason. I don't know why, but a set of vectors, I shall call it W, in Rn is a subspace when, and there are three laws. I'm going to label them differently to the way your lecturer labels them because it's easier for me to remember them that way. There is law 0 and law 1 and law 2. Law 0 is that the 0 vector is in your set. That is not enough to make something a subspace, but you definitely need it to be true or it's not a subspace. And law 2 is that if there is a vector in your subspace and you have a real number, I shall call it k, then when you multiply it, you're still in the subspace. This says you can't escape W by doing scalar multiplication. It's self-contained. And if U and V are in W, then when you add them, the new point that you make is also in W. So I just want to be very careful about this. So at the moment, this W is a point, this little W is a point. And then to do the scalar multiplication, I have to think of it as an arrow. But then this one, in order to tell if it's in W, I have to think of it as a point at the end of the arrow and color that in and see if it's really there. So the reason I call this rule number 1 is it uses one vector, and this is rule number 2 uses 2 vectors. And rule number 0 uses the 0 vector, which is technically a vector, but whatever. And that's why I put them in that order. That is the definition. And this is trying to get at the idea that it has to be self-contained with respect to the things that make vectors vectors. Stop there for a moment. Thoughts, feelings? Okay, cool. So the reason why a span produces a subspace is because you made all the linear combinations that you could make out of those 2 vectors. And so therefore you can't escape by doing more combinations because you made them all. That's why. Now, that description there does not sound like a math proof, but it's the reason why it works. You say, well, I'll just make all the combinations and that will cover them all, and so I won't be able to escape. It's very nice. So this definition doesn't automatically make you feel like, it definitely shows that the idea of spanning will produce a subspace, but it doesn't definitely prove that all subspaces must be the span of something. But it does turn out that that's the truth. Because once you have some vectors in a subspace, the entire span of those vectors has to be inside that subspace because it's self-contained under the act of spanning. Because these 2 actions here together is what spanning is. So, yeah. Okay. So what this means is that there are things that you can tell are subspaces based on the way they look. So telling something is a subspace you can tell what something's a subspace is based on how it looks. It doesn't feel like the sort of thing you're allowed to say in an exam as the reason why. You say, well, it doesn't look right. That doesn't sound right as the kind of thing you can say in an exam. But you can say all subspaces in R2 are lines. It's not a line. Therefore, it's not a subspace. So that's useful to know. So subspaces are just the origin all by itself. That is the most basic kind of subspace because it's self-contained, because no matter what addition and scalar multiplication you do to it, you can't escape it because you'll just get 0 as the answer every time. So that is the smallest subspace and is the only subspace that is a single point. And lines. through the origin. They have to go through the origin or they won't satisfy the zero law. And they have to be lines because we know that when you do any scalar multiple of something that's on a line, you just get the rest of the line. And, you know, planes through the origin and three-dimensional spaces through the origin. This is where your imagination tends to give up, thinking about three-dimensional spaces that don't cover the whole of four-dimensional space, like what the hell, but that's okay because they all look similar anyway. And these are, in fact, all the subspaces. They all look like that. So if you're in two-dimensional space in the plane in R2, these are all the subspaces. And the only plane through the origin in R2 is the entire of R2, which is technically a subspace because it is self-contained. There's just nowhere else to go. Yeah. And so if it doesn't look like that, it's not a subspace. So when you see something like this, the set of vectors called with coordinates x and x squared such that x is in R, that is totally a parabola because y equals x squared. And that is not a line. So if you were in an exam and someone said, is this a subspace? Then give a reason. You would say that is a parabola, and all subspaces in R2 are lines, so it is not a subspace. That's a perfectly good reason. Use a lot of words. If someone said, prove this isn't a subspace, you probably have to use the definition of subspace. Most proofs have to use the definition. So I know this isn't a subspace because if I pick any point on this curve, like 1, 1, and multiply it by a scalar to get like 2, 2, I'm not on the set anymore. So when I multiply one of the vectors on there by a number, it produces a point that's not in the set. And so it's not a subspace. So if you wanted to prove it, you would say 1, 1 is in, oh, let's give it a name, W since x equals 1 gives 1, 1 squared. Yep. 2 times 1, 1 is 2 times 2, 2, which is not in W, since if it was, x would have to be 2 based on the first coordinate, and the second coordinate would be x squared, which is 4, but it's not, it's 2. Yeah, that was hard work to write that down in a way that makes sense. But since if it was, then x would be 2, and the second coordinate would have to be 4, and so it's not. In case you've never seen this symbol, you should have, I hope. But if you're watching this in the future at the beginning of Maths 1A because you want to get ahead, this symbol is read aloud as in, or is a member of, or is an element of, or which is in, or be in. You can conjugate that verb in whatever that verb of being in whatever way you like. So this is read aloud as 1, 1 is in W. So that was read aloud as is in. Yeah. Rightio. And this is not in because we crossed it out. And so it doesn't satisfy law number 1, the scalar multiplication law. It also doesn't satisfy the addition law. But you only need one vector to break the scalar multiplication law, and so it's the easiest one to break. Okay, that's how it looks. It's worth noting subspaces don't have gaps in them. So that set is not a subspace because of this gap. I could pick a point here and multiply it by the correct scalar, like a half, and it would fall into the hole. Or I could multiply it by 7 and it would fall out on the outside. Subspaces don't have gaps and they go forever. Now, you can't just say, as your reason that it's not a subspace, it has a gap. You have to do a working like this to show that there is a vector that when you multiply it, falls into the gap. But in your head, you can say gap and doesn't go forever. So not subspace. Because there is one subspace that doesn't go forever, which is just the origin. So, but it definitely doesn't have a gap. It's only got 1 point. So yeah. Okay. How are we feeling? Awesome. So it is possible for things to satisfy one rule but not the other. You can satisfy scalar multiplication, but still satisfy addition. And not satisfy addition, and you can satisfy addition but not scalar multiplication. Things that satisfy scalar multiplication tend to look like stars. They're like lines through the origin. Because if you can do scalar multiplication, you can go as far in and out as you want. And so scalar multiplication things, scalar multiplication tends to produce things that look like stars, and addition tends to produce grids. Damn it, didn't do that very well. I'll make more. Tends to produce a grid of dots like that. Because if you can only add things, actually you only get them in one direction, actually, because you can't do subtraction. But anyway, that's things that satisfy addition tend to look like grids. Things that satisfy scalar multiplication tend to look like stars. And if you want to do the stars that go with every point in the grid, you'll fill out all the rest of space. And so just in case you were wondering. Yeah. All right. We're doing okay. So that is what subspaces look like. There are two other ways to see subspaces. Maybe it's only one more way from how it's written. There are 3 ways to write sets, technically 4. There are 3 ways to write a set without referring to an existing set. And you can write it as a list, like I did before. The only subspace that's a list is the 0 vector. Because once you have 2 vectors in it, then that will cause you to have to do all the stars and you'll get infinitely many vectors. So if you've got a finite list of just some vectors, then it's not going to be a subspace. So that's that. There is like a short, kind of like a list, but there's infinitely many things in it. So you can tell how to construct it. And so that's something like that's a construction. What it is, it says, here's how to make a vector out of some coordinates or whatever. And here's just some technical details about what numbers we're allowed to choose for that. This is a set by construction. And the only subspaces that are sets by construction are the ones that are spans. Because the span is technically a set by construction because you know what vectors are in the set by how you make them from the other ones. So I'm just going to do this one first. I'm going to change that to a T. I can rewrite this as a span. So I can split it up into a vector of just the bits involving T and a vector involving just the S. And then I can bring the T out the front and the S out the front of that one. And lo and behold, it's linear combinations of these two vectors. This thing is the span of these two vectors and is therefore a subspace. But if you don't have all the linear combinations and you've only got some of them, then it's not a subspace. One, 5t s plus t. I'm going to make that first coordinate a 1. And when I do this same trick, I get that. And I don't, there's 3 vectors involved here. And I can't make this first one out of either of the other 2 because these both have zeros in that first spot. And so I do not have all the linear combinations of these 3 vectors because there's no letter just here. It's not all linear combinations, and therefore it's not a subspace. Also, the 0 vector isn't one of these options because all of these vectors have 1 as their first coordinate, so you can't make the 0 vector this way. But I just want to make this argument because you can make this argument because sometimes the 0 vector's in there and it's still not a subspace because you haven't got all the combinations. And one last example of not having all the combinations. Exactly the same as the previous one. 5t s plus t, 5t s plus t. But the s and t are not all the numbers in R, they're only the numbers in Z. So it's, again, not all the linear combinations. In particular, this vector is in there. That's making t equals 0 and s equals 1. But this vector is not. So I multiplied by a number and I got a thing that's not in there anymore. So that's the proof. That's the thing in your head. Yeah. There have been in exams questions where they didn't ask you to give a reason. They just said, which of these are subspaces? And there's a Mobius question that does that too. It might not be in Maths 1A. It might be the first Mobius in Maths 1B. That just give you a list of like 10 sets and say, which of them are subspaces? And you can look at it and go, not all the combinations. No one asked me to give a reason, so I'm just going to say that one's not. Yeah. How are we feeling? Awesome. No? Do you want to ask something? Yep. Yep. This one wasn't a subspace. Yep. This one is a subspace. Yep, because I rewrote it as a span. So I took this vector and I rewrote it like t of something plus s of something. And because the t and the s can be any numbers at all, that means it's the same as spanning. So since I can't have any number I want there, I can only have a 1. Yeah, because I wasn't allowed to do all of the numbers in these spots in front of the vectors. Correct. And when you say collection of all the new combinations, that is what span is. Yeah, and subspace, they are the same thing. But spanning is an action and subspace is just an object. Span can be both an action and an object, but the word subspace is just an object. You don't subspace things. You just make subspaces. So I guess maybe that's why we have the word span, because it's a verb. Spanning is the action that produces subspaces. Yep. Mm-hmm. Yeah. That gives you the curve.
What was that? That would prove that if it was x and x, then it would be linear, but if obviously it's x and x squared, it won't be.
Yeah, so I'm going to repeat that. If it was x and x, it would have been a straight line. If it was x and x squared, it's a curve. But I was actually I was doing kind of even less than that. I was going, well, I definitely can show that 1, 1 is in the set. And instead of making a new point in the set by subbing in a new x, I'm going to attempt to make a new set by timesing that vector by something. So I'm going to do a scalar multiplication and attempt to make a new vector by timesing it by something. And when I made a new vector by timesing it by something, it didn't produce the vector it should have by subbing in 2. This is 100% a proof that this is not a subspace. So yeah, this is a classic proof. And the short version is, if you have things here that are not just this sort of thing where they're like just multiplying and adding inside the coordinates, then you can use that scalar multiplication proof. The only problem is that when you have both of them as squares, then the scalar multiplication works fine. So you have to use the addition as the problem, unfortunately. So the problem with these things is they all sound simple, and then you start looking at the examples that are just a little different, and no, it's not. So it's useful to start seeking out as many examples of those things as you can, so you can know where the edge is. Yeah, these are good questions. They are the right sorts of questions to get a handle on. Well, what actual method did you use, and can I reuse it in a new situation? That's an awesome way to think about maths. So yeah, thank you for asking that question, because I can make that point. Okay, last thing. I don't know what it is. I'm just going to call it rule. There is one more way to make a set, which is a set by rule, where instead of telling the person that's reading it how to make all the vectors in the set, which is what this is saying all the vectors in the set can be made in this way. What it says. So there's another way to make a set, which is to tell people not how to make any of the things in the set, but just how to decide if something is in the set or not. So just as an example, the set of x, y, z in R3 such that x plus y is equal to z. No, I'm not going to do that. X plus y minus 2z equals 0. Let's do that. This doesn't tell me what any of the points in this set are. It says that they're all in R3. That's a good start. But the way to decide if they're in the set is that when you sub in the coordinates, it produces 0 when you do this. And does anyone know what shape this set is? If I colored in all the points that satisfy this equation, what shape would it be? It's okay not to know. I just want to know. What's that? It is not just the origin, though the origin does work. So 0, if I put 0, 0, 0 in this spot, I will get 0 plus 0 minus 2 times 0, which is in fact 0. So it does in fact pass through the origin. That's a good, at least it satisfies rule 0 for being a subspace. It's a plane. One equation, one linear equation in R3 makes a plane. And you just said that the origin is in this plane. It's a plane through the origin, which means it's a subspace. Yay, yep. Yep. That's a great thing. What if you had some restrictions on this plane so that it didn't go forever? X, Y, Z in R3 such that X plus Y minus 2Z is 0 and X squared plus Y squared is less than 5. Something like that. And this plane doesn't go forever because I can't make my X and Y coordinates as big as I want. Not subspace. And so the proof that this is not a subspace, like in your head, you're going, doesn't go forever, not a subspace. The proof for this is that you could try and think of a point that is in the set. Oh man, 1, 1, 1 is in this set. So 1, 1, 1 is in this set. Since 1 plus 1 minus 2 times 1, I sub the 3 coordinates into the equation, does in fact come to 0. So that is definitely a point that it is in this set. Cool. It's almost as if I set that up that way. But if I multiply this by a big enough number, it won't satisfy this equation anymore. Well, that's not an equation, but that inequality. So 1 squared plus 1 squared. Oh, no, wait. And 1 squared plus 1 squared is 2, which is in fact less than 5. So it has to satisfy both of them to be in the set. Okay, but scalar multiple, let's go 3, 3, 3. That's a scalar multiple of this vector. So I'm thinking this is one of the vectors in my set. Instead of trying to make a vector that's in the set, I'm just going to scalar multiply and make a new vector and hope that it's in my set or wonder if it is. But 3 squared plus 3 squared is 18, which is not less than 5. And so it's not in the set. And so therefore it's not a subspace. This would be the proof that this thing isn't a subspace. This bit's the proof. Because it directly uses the definition, and so it doesn't satisfy the scalar multiplication rule. But this one is a subspace. No matter if you've got something that does satisfy this, then if I multiply it by something, it'll still work. If 1, 1, 1 works, 1 plus 1 minus 2 times 1 is 0, then 3 plus 3 minus 2 times 3 still 0. And that proving that this is a subspace is a lot more work than just telling whether it's a subspace. I know it's a subspace because it's a plane through the origin. In fact, even better, I know it's a subspace because this is a homogeneous linear equation. If you make a set by rule, and the rule is any number of linear equations that are equal to 0, homogeneous linear equations, then it's definitely a subspace every time. So you've got vectors in Rn X in Rn such that homogeneous linear equations is always a subspace. If they're not homogeneous, not a subspace, because the 0 vector is not in there. And if they're not linear, not a subspace. Well, not usually, because it breaks the scalar multiplication rule. And if they're not equations, not a subspace, usually because it doesn't go forever. Because we had one, this isn't even an equation. I wouldn't expect that to be a subspace at all. They have to be equations. Just be careful, sometimes nonlinear equations are still subspaces because the only way to satisfy them is for to be the zero vector. So classic, this one is like psych, x, y in R2 such that x squared plus y squared equals 0. Psych, that's only the zero vector, subspace. So even though this is not linear, there's only the zero vector that satisfies it, so it's still a subspace. Only 0, 0 is in this set, therefore subspace. So that's just like, okay. So I've been talking for a while, but I just wanted to get a real handle on this. If you go look at some old revision seminars, you'll find me doing this whole spiel multiple times. I wish it was one of the videos in the course, but one day, maybe in the new university, I'll convince them to let me do that video for them. I'll cut, that's on the recording. Well, if you're listening to this, you know what I want to do. How are we feeling? Feeling a bit better? Good. So we have 3 ways to define a set. And each way has a particular type of thing that definitely makes a subspace. Okay. One last thing. Basis. We did basis, didn't we? Yep. Okay. The point of a basis is to rewrite your subspace as a span. All subspaces are the span of something, and the something is called a basis. If you want a way to prove that something's a subspace, a full subspace proof, I can do that, but I did want to talk about the calculus first. So I may come back to it, but otherwise you can find them in Maths Learning Center's YouTube channel. So the point of a basis, like all subspaces, are the span of something, and this something is called a basis. That's what a basis is for. Now, batteries not included. Not all somethings that can go in that spot are bases. But that's what the purpose of a basis is, to be the thing that spans your subspace. And there are many ways to choose something that spans your subspace. Like if you're in the plane, you can pick any two. If you're in the plane, you can pick any 2 vectors that point in different directions, and they will span the plane. Some of them are better than others. You can pick 3 vectors if you want, and they will span the plane, but you don't need 3, you only need 2. So the point of a basis is not just to be something that spans the plane, but the shortest list of things you can that spans the plane. And the way that we organize it to be the shortest is to say that they are linearly independent. So the definition of a basis so the vectors v1 up to vk is a basis for the subspace W when, so rule number 1, they span W, which is short for saying W is the span of those vectors, which means that every vector in W can be made as a combination of those things. And 2, they are linearly independent. I would like to add secret rule 0, which is not a secret at all. But secret rule 0 is they can't span it if they're not in it. They have to be in W to span W. I mean, they always span something. It just might not be the thing that you want. So any collection of vectors will span something. They just need to span the subspace you're thinking of for it to be a basis for that subspace. And it's useful to know that you can't just be a basis all by yourself. You're always a basis for something. Well, technically you can be a basis, but you're always a basis for something. But you have to be thinking of a subspace first to have a basis for it. A basis is a piece of information about a subspace. And it turns out, and you don't get told this until Maths 1B, again, something I'd like to change. If you want to span a plane, you're going to need 2 vectors. If you want to span a line, you only need 1 vector. And if you want to span 3D space, you're going to need 3 vectors. If you want to span 14-dimensional space, you're going to need 14 vectors. Too many vectors, they'll be linearly dependent. Not enough vectors, they won't span. And for future reference, the correct number of vectors is called the dimension. So a plane's a 2-dimensional object, you're going to need 2 vectors. That's the idea. Yeah. So, but that's not in this course at this time. So yeah. So that is that. And that's what a basis is. And so the important thing to know about a basis is the first thing you have to make it do is span. Being linearly independent won't help unless it spans already. So that's why spanning is rule number 1, is they have to span first. Once they span, then you can fix the linearly independent thing after. But I should probably say what linearly independent means. Linearly independent means that none of them is a combination of any of the others. That's what it means. That's not the definition, but that's what it means. So this is the truth. It is in fact true that that's the way to be linearly independent, that none of them is a linear combination of any of the others. And the reason that means that is like, well, if one of them was a combination of some of the others, you wouldn't need it if you were spanning because you could make it out of the other ones. And so it would still be in the span eventually. You just don't need it in the original list because you can make it. Yeah. Just like I don't necessarily have to list cake as a thing I have if what I have is flour and eggs and sugar and milk. Yep. Yep, of some of the other vectors. So none of the vectors in the list is a linear combination of the other vectors in the list. That's what linearly independent means. And so, for example, 1, 0, 3, 2, 1, 5, and 12, 1, 35 is not linearly independent because this one is 10 times that one plus that one. No, 10 times the first one. So since this one's a combination of those two, they're not linearly independent. But if I just changed one of these numbers, like made that a 36, they would be linearly independent because the only combination of these two that matches the first 2 coordinates is this one, and it doesn't match the 3rd coordinate. But that takes a lot of effort to describe. which is why we have a definition of linear independent that doesn't talk about none of them being a linear combination of any of the others, because if you've got like 10 vectors, that becomes very difficult to check. And so our definition is easier to check using the standard method of solving all problems in Maths 1A algebra, which is row operations. The definition is that the vectors v1 up to vk are linearly independent when the only solution to x1 v1 plus all the way up to xk vk equals the zero vector, that equation, which has unknowns in the spots that where the coefficient of the scalar multiples go, is that every one of them they're all zero. That's definitely going to be a solution no matter what. You can choose all the coefficients to be zero and you will get the zero vector, but to be linearly independent, that has to be the only way to make the zero vector. That's the definition of linearly independent. And the reason it is chosen as the definition is because it's the easiest one to check using row operation. Also, it's the easiest one to prove in a proof. Mathematicians are all about proofs. So it's easy one to prove if you don't know what the vectors are. And so the definition is this, and what that means is that if you have some vectors like that, and you want to know if they're independent, the quickest way is to attempt to solve this equation. And when you attempt to solve that equation, you have to put your vectors in as columns because it doesn't work otherwise. And you end up with this. Technically, you are trying to solve this. You don't need the 0, 0, 0 because every time you do a row operation, it will stay as a 0, 0, 0. So you don't technically need that bit. So you can just put them as columns in a matrix and you can row reduce until you can tell whether there is a unique solution or not. There will always be a solution, but you want to know whether there's infinitely many or not. And so in this situation, I'm not going to do it because I know that they're independent. It'll come down to here, and this tells me that the first x in this equation is 0, and the second x is 0, and the third x is 0. Therefore, they're independent. What you need is one of these pivots, one of these in every column. You don't need one in every row because your vectors might have like 10 coordinates and you might only have 3 of them. You don't need one in every row, but a pivot in every column means they're independent. But if you have even one column with no pivot in it, they'll be linearly dependent. So back here with this one, when I had 1, 0, 3, 2, 1, 5, and 12, 1, 36, what would have happened when I did that? So 35 before, I would have gotten some numbers in these spots here, like that. That's what would have happened. And there would be, this column has no pivot, and so therefore they're linearly dependent. But the cool thing is that if I just crossed out this entire column, now I have two vectors that are linearly independent because their row operations do produce a pivot in every column. And so if you just remove the original vectors that produce the columns with no pivots, then you will make something that is independent. And that's a useful thing to know. Yep. Yep. To do this process, you have to put them as columns. And in fact, all the processes in Maths 1A that decide about vectors, you need your vectors to be columns. Because of where you put them in relation to the matrix that's nearby. So yes, that was a very important question. There is one process in Maths 1B that allows you to have them as rows, but in Maths 1A, vectors are columns and equations are rows. If you're very, very lucky and you have the same number of coordinates as you do vectors, then sometimes if you put them in as rows, it coincidentally works out okay. But I wouldn't trust it. So it's put them in as columns and look for pivots in the columns. Yeah, but that's because, yes. And so equations become rows, vectors become columns. And that took me a while to get when I was in first year. But I mean, it's really deep, actually. If you talk to some of the physicists and mathematical physicists, like, yeah, like deeply, equations are rows and vectors are columns. Like it's a whole thing. Yeah. Okay. Cool. And so that's final thing. One last thing is, how do you in fact find a basis? I'm going to have two situations. Three, actually. We had those three different ways of writing a set: as a list, as construction, and as a rule. Each of them has their own way of finding a basis. So, list. There is only one subspace that is a list, and it is this one, and that has no basis. Or if you like, the number of vectors in this basis is 0. And the reason it has no basis is that any list of vectors that has the 0 vector in it is linearly dependent. If you have like 15 vectors and then the last vector is the 0 vector, that list is linearly dependent because the 0 is automatically a combination of whatever you want because it's 0 times all those things. So the 0 vector is the only subspace that doesn't have a basis, because it is impossible to span this with a linearly independent set. Yep. But that's okay, because it's a 0-dimensional subspace. It's a point. Points have 0 dimensions, so therefore you should span them with 0 vectors. Yay, everything fits together. It's nice. I like it. So that's that one, but I just thought it was worth mentioning. So if your set is defined by construction, the first thing you need to do is rewrite it as a span. Okay, you should always rewrite it as a span. And if it's already written as a span, and that's the only example I want to do, I'm just going to use the example I already had. So this is my subspace. I know it's a subspace because it's a span of something, and all spans are subspaces. And in order to be a basis, I need to be able to span my vectors, my subspace with it. So I already have a set of vectors that spans my subspace, so it's a good starting point for making a basis. So I already know that the vectors 1, 0, 3, and 2, 1, 5, and 12, 1, 35 span W. That is definitely true. So we're halfway to being a basis. The other half is they have to be independent, but they're not independent. but that's okay. I know which of these two vectors are independent. It's the first two, because when I did my row operations, so what I need to do now, choose the most linearly independent vectors from this list. And so when I put them as columns, and I did my row operations, I got that, which tells me that they are linearly dependent. And I get my pivot columns and I go back to the original ones and they are my basis. So that is how to find the basis for something that's already a span. You stick them in as columns in a matrix so that you can row reduce to tell which of them are independent. Remove the ones that don't have pivots at the end, and they are your basis. And the reason that they are is because, well, if they're independent, if they're linearly dependent because the third one is a combination of the other two. And so I don't need it because it's already part of the span of these two. So once you've written it as a span, then you can do this process. And last but not least, by rule. So we know that the only way to make a rule that, not the only way, but you can always rewrite a rule as linear equations if it's a subspace. So my example is going to be this. So I have x plus y, z, w. It's technically in R4, but I couldn't be bothered writing that bit. X plus y is 0, and also y minus 3z plus w is 0. So this is a subspace of R4. Saying it's a subspace of R4 does not mean it will need 4 vectors to span it. It just means that it has vectors with 4 coordinates. So the only way to find a subspace is to span. So I have to rewrite this subspace as a span in order to find the basis. And the only way to, to tell if something spans, you have to know that every vector in this subspace is a combination of the things that you want to span it with, which means the only way to tell if you have a span is to find all the vectors. So this is the first thing to know is that if you want to know a basis, you have to know what all of the vectors in your subspace are. And this doesn't tell me what the vectors are. It just tells me how to check if something's in this subspace. If you told me a vector, I could sub it into the equation and say, yes, comes out to 0 in both equations, definitely in the subspace. Or, no, second equation came out to 10, not in my subspace. Or first equation came out to 15, not in my subspace. So it doesn't tell me what the vectors are. I have to find the vectors. And to find those vectors, I have to solve these equations. And I know how to solve equations, row operations. So I'm going x and y and z and w, and the answers are 0 and 0, 1x and 1y and no z's and no w's, and no x's and 1y and minus 3 z's and 1 w. So you were asking before with equations, they become rows. And my goal is to solve these and find all of the vectors that satisfy these equations. So I need to do row operations, or not, if I'm very clever, to get to a point where I can find what all the vectors are. I'm going to tell you a secret. It's not a secret at all. When you did convex sets and slack variables, that was in this course, right? You learned So when you first learned about row operations, you went, yeah, I have to go to the reduced echelon form. I need to make my little staircase, and that's great. But when you did slack variables, you learned that you don't actually need to do that. You just need to create all the columns of the identity. It doesn't really matter what order they're in, and it doesn't really matter how far apart they are. There is a column of the identity here, and there is a column of the identity here. If I was doing slack variables, I would make these two 0, and that would do the thing. And so I don't have to do any row operations. Yay! I can just make these the free variables. Isn't that cool? I'll do the other one as well, but I just wanted to show you because that's fun to me. So I'm going to say let y be equal to s and z be equal to t, and then I have 1x plus, then x, 1x plus 1y, but y is really s, is equal to 0 eventually, and so that means that x is equal to minus s. And then I have no x's and 1y, but y is equal to s, and minus 3t's, but minus 3z, but z is equal to t, plus 1w equal to 0, and so therefore that means that w is minus s plus 3t. And so my vectors are in fact minus s and t and minus s plus 3t, like that. So what I've done is I've taken what x is and put it in the first coordinate, what y is and put it in the second coordinate, what z is and put it in the third coordinate, and what w is and put it in the last coordinate. And that is s lots of minus 1s and 1s and no s's and minus 1s, and t lots of no t's and 1t and 3t's. And look, that's a span. And so therefore, my w is in fact the span of these vectors. That's what it really is. And therefore, that's the basis. But David, you're supposed to check if they're linearly independent. That's okay. This process always produces linearly independent vectors. So you are supposed to mention that they're independent. I know they're independent because of this bit just here that looks like an identity matrix. Because if I put them as columns, because of that little identity matrix bit, that would produce pivots in both columns. So that's nice. So right. But this is not the way to do it. Any way of getting that two identity matrix columns in here would do the trick. So I could have, just to be absolutely certain that I know what's going on here, that you know what's going on, I could just as easily have done, that's x, that's y, that's z, that's w. I have to put the names of the variables in above the columns or I forget. So, because there's been courses where they put the w before the x, which makes sense because they're in alphabetical order. But it freaks me out when the first coordinate's not x. But if I write them, I don't forget. If I felt the need to do traditional reduced row echelon form, I do have the first column of the identity already, and I would normally put a pivot there. And so I would do row 1 is row 1 minus row 2, and I would get, I didn't change the second row. And then 1 minus 0 is 1, 1 minus 1 is 0, 0 minus 3 is plus 3, 0 minus 1 is negative 1, and 0 minus 0 is 0. And now I have my two pivot columns, which is great. And I would say let z be s and w be t. And now x is minus 3s and plus 1t. Yes, because this is like plus 3s minus t, and I put them on the other side. Okay, it's all good. If you do it a lot, then you can really concentrate and get it right. And so the y is 3s and minus t. And so I get that x, y, z, and w is minus 3s plus t, 3s minus t, s, and t, which is s times minus 3, 3, 1, 0, and t times 1 minus 1, 0, 1. And that little identity matrix bit when you do traditional reduced row echelon form, it tends to fall at the bottom of the vectors and be a little easier to see. And so therefore a basis is -3, 3, 1, 0, and 1, -1, 0, 1. One of the annoying things about mathematicians is that even though the vectors are technically supposed to be columns, we write them as rows sometimes and don't bat an eyelid. Some lecturers are really precise about it and put a little t here to say that we have to transpose it to make it a column. That's what they're doing when they're doing that. Yeah, you will notice that this basis is not the same as this basis. So this vector is minus that vector. The people who run your course are clever enough to be able to tell if the thing you've got really is a basis. They will be okay with everyone producing a different answer. I mean, they might be a little frustrated and go, oh my God, they've all given different answers. But, you know, that's their fault. Plus also, if you give the one that's a little bit different, they'll slow down and go, oh, that was pleasant. Anyway, whatever. As a marker, I always liked someone who did a slightly different method because it was less boring. But some markers don't like it to be less boring because they just want the whole process to be over quicker, which I totally understand. You don't like doing exams, they don't like marking exams. But unfortunately, they are the only way that these guys can think to test what one person knows, rather than a group of people or one person and a chat bot. So, yeah. Anyway, exams are going to be a thing, unfortunately. Okay. How are we feeling? It was a whirlwind tour of that bit of the course. I've skipped a couple of things. Haven't done a proof that something's a subspace. But I did want to talk a little bit about the two fancy flavors of integration techniques, since people asked. And I know I've officially only got 15 minutes, but I can go over. If you have to leave because you've got to move your car or whatever, then I won't be offended if you do. Okay. So, all right. Give me a moment and I'll just... Okay. There are two fancy integration techniques at the end of your integration techniques section of this course, which was like the very last thing, right? Yep. And I would like to talk about both of them at least briefly. But before I do want to remind you of the less fancy integration techniques. My list of integration techniques that you should think about trying in the order that you should try them in is technique 0 is not a technique, it's just do it. Which means, oh, look, it's x cubed. I will put the exponent up by 1 and divide by the new exponent. I can do that. Oh, look, it's cos, it's plus sign, and so on. You just know the answer. Like, let's just do it. Number 2 is rewrite it. As in, like, expand the brackets, or maybe sometimes factorize, maybe use a trig identity, whatever. Do whatever you want to do and rewrite it so it looks like something you can just do. That is technique number 1. They do not usually list this as a technique, but it really is. Classic as well. You see 1 over x squared and you go, oh, that's x to the -2. I can now put the exponent up by 1 and divide by the new exponent. All of those things are rewriting it. Technique number 2 is substitution, which is specifically designed for when one part of the expression looks like the derivative of another part, or there's just something inside another function. And then technique number 3 is integration by parts. They are the less fancy techniques. They are the bread and butter of integration. And the basic idea of all 3 of these is to turn it into something that you can do, that you can just do. None of these do the integral, they just turn it into another integral. Okay. So, trig substitution is a kind of substitution. It's this one, but it's fancy. So, technique number 4, trig substitution, which is fancy substitution. And it is specifically designed for a specific kind of expression that you see in your function, but you shouldn't do it unless you've already ruled out these as good options to try. So do not do trig substitution if an ordinary substitution will do the trick. Do not do trig substitution if you just happen to recognize that it's already the derivative of something that you've calculated in the past. Classic exam question in high school is like, differentiate this, and then like 2 pages later, integrate this, which happens to be the thing that you differentiated before. You go, aha, it's just the answer. So just, that's one of, I wrote a question like that when I wrote a year 12 exam. Classic, I love it so much. So trig substitution is fancy substitution, and it's designed specially for things that look like they could have come from Pythagoras's theorem. So things like, you know, something like that. Expressions that have that sort of thing in them are excellent trig substitution fodder. And the other common one is when the x is on the hypotenuse. No, one more. So I'm going to maybe put a 4 there and an x there. And then this is root 416 plus x squared, and that sort of thing. And the only other one is the one where the x and the 3x is on the hypotenuse. No, yep, x is on the hypotenuse. And so this would be like 4x squared minus 4. So these sorts of expressions that look like they came about from a trig from Pythagoras's theorem, they are the expressions that will flag to you that you need to do fancy trig substitution. They do not have to be under square roots to be useful, but usually they are under square roots, because the ones that are under square roots are particularly annoying. And what you would like, the vibe of these is that you would like to rewrite this expression under this square root as something that is already squared, so that you can square root to square and make it go away. That's the goal. So the goal, use trigonometry to rewrite this bit as things squared so that it can cancel out the square root. That's the goal. Problem is, what you're doing is you're doing substitution, so you're going to have to, because you don't get a choice, change the dx along the way. Or the whatever the variable is along the way, because it's substitution, and that's how substitution works. That's the goal. This helps me to notice when I'm supposed to use it. Because if there's been a classic, every other semester, there's a question in the exam that just says, here are 3 integrals, do them, and it doesn't tell you how. So if you have to use trig substitution, you're going to have to be able to tell that that's what you need to do. Not every semester, because they mix it up. as I said, you know, nobody likes to do the same thing 10 years in a row. Some people do, though. You know, personally, I like wrapping Christmas presents. It's the same every time, but I know how to do it, and so I like doing it. But I only do it once a year, so I guess that's okay. Maths 1B, you do 3 times a year, and you can, oh man, you can get a little tired of it, I can tell you. So not to say I will not help you if you don't come to Maths if you come to the Maths Learning Centre, but for Maths 1B, so it's fine. Okay, so trig substitution is designed to that, and we're going to use trig identities to rewrite this as this. And you have to pick the right trig identity. And there are 2 ways that people have of picking the right trig identity. One of them is by drawing a triangle like this, and the other one is by just writing down the trig identity. Pardon me. Officially, you're supposed to write down the trig identity even if you do use the triangle. So only way to do it is with an example. I don't know. This may suck royally. I shall do this one. Now let's make it worse. Yeah, okay. Yes, this may be very bad. But at least if we can do this, we can do anything. So I look at this and I go, Huel, I notice the Pythagoras-ish thing. And so trig identity, trig substitution seems like a go. I should just do a quick check to see if ordinary substitution will do the trick. If I made u equal to this, then the derivative would be 2x. And I'd need like just an x somewhere. Damn it, it's an x squared. If that was an x cubed, ordinary substitution might have helped, actually. Because if this was u, I could rewrite the x squared as something involving u, and then the extra x would have come from the du. So that would have actually worked. But the fact that this is an even number, it's just, yeah, that's my problem. So I'm going to try trig substitution. And I'm going to try trig substitution, but I am not going to, at the first thing I write is what u is. Your lecturer probably uses theta. I don't, I just use u for everything. So just, you're going to have to cope. So I'm not going to say what u is, but I am going to write down the trig identity that I hope will help. And the only trig identity that has squares in it that I can remember off the top of my head is this one. That is the fundamental trigonometric identity. I have left a bit of space because I'm going to fill in a bit of working just here. And I have written it in alphabetical order, cos and then sine, like C and then S. Because if I was doing hyperbolic trig substitution, then it would have been cos squared minus sine squared, and they would have to be in that order or it would be wrong. And so I always do cos and then sine, so that when in the rare situations when I do hyperbolic trig substitution, I don't get it wrong. Also, cos is the x coordinate and sine is the y coordinate. So if they're in alphabetical order, then that matches up with that too, which is nice. Doesn't work in French, but that's okay because they have different names in France. So yeah. Anyway, here we are. That doesn't look right to me. What I want something with a plain number plus something with a variable. And I want it to come out to something with a variable. And so if I move this around so that I do have a plain number and a variable on the same side, that would have been 1 minus sine squared. And it has a minus that goes with the variable, so that doesn't work. So I need the other one. And the other one is found by dividing this by cos squared. And cos squared divided by cos squared is 1. And sine divided by cos is tan, so this is tan squared. And 1 divided by cos is second, so this is sec squared. You see how my brain works? I tend to remember some things and then remember other ones by connection. This one's looking good. I have a plain number plus a variable squared. That's what I've got here. But I don't have a 1 in this thing. I've got a 9, so I'm going to multiply everything by 9. Cool. And so what I need is for this to be x squared, because then that will match up to this. And so that's what I'm going to do. I'm going to make x equal to 3 tan u. Some people who have extremely good memories, better than mine, can look at this and just remember that this is what they're supposed to do. But I cannot. So this tells me what I have to do. Okay, and so if this is 3 tan u, that means that I'm going to have to do somewhere along the lines that x, I have to write somewhere. I'm going to put it here. X squared is 9 tan u squared. And so this is 9 plus x squared is 9 sec u squared. And so therefore root 9 plus x squared is 3 sec u. Sweet. So let's have a look at what we've got. We have dealt with the root 9 plus x squared. We know what that is. That's 3 sec u, so I can sub that in. And we have dealt with the x squared. That's 9 tan u squared. That's great. We're going to have to deal with the dx. Traditionally, in substitution, you deal with that first. That's why I've left a little space here. So the dx is going to be differentiating this with respect to u, which would be 3 sec u squared and then du. So I've done 2 steps of working. It's taken me 20 years to be able to do this. Normally I'd write dx on du equals and then move the du, but I'm now can do it without that and go straight to the dx equals something du. About half the time. So yeah, okay. So now I have, just to be clear, I have dealt with this bit that's here. I've dealt with this bit that's here, and I've dealt with all of that that's here. And so I can now replace every part of my integral with something new. So the 5 is still there because it's just a number. And then we have 9 tan u squared. And then we have down here 3 sec u. And then here we have 3 sec u squared. Wow, that sucks. But anyway, sorry. I may not finish it from here. I guess the 3's cancel. One of those secs can cancel with one of those. Tan squared times sec. Cool. Not a fan. Not a fan at all. I do not like it. I'm pretty safe to say that they would not ask you to finish this in an exam. So at this point, we have now turned it into something that is supposed to be able to be done by the less fancy method. So you could probably a trig identity will turn it into something that is possible. I guess the tan squared we know is sec squared minus 1. So I could turn this into something with a sec cubed and a sec, which would require you to integrate sec and sec cubed. Sec cubed I can do because it's sec squared times sec, and I can use integration by parts because the integral of sec is squared is tan. Nope, nope. I choose not to do this. I would literally in an exam say possible, or go looking to see if they had a hint which had told me what the integral of this was. So it doesn't always turn it into something that you know how to do yet, but it does turn it into something. But you can imagine an exam question that says, turn this into an integral involving theta or u, and stop. Classic exam thing is just get you to do half a problem. So yeah. Should have done one that turned out something. All right. Let's try another one. No. Let's do that one. So, classic, weird thing under a root. Derivative's not there. So I'm going to have to use trig substitution. So, all right. Cos u squared plus sine u squared is 1. Yeah, that's going to look right. We've got number minus variable squared, it matches up. And so I really would like that number to be a 4. Right. And so all of this is supposed to be equal to 9x squared, so that they match up directly. So what I need is, so we need 9x squared be equal to 4 sine u squared. That's what we need. And so working backwards, we need 3x to be equal to 2 sine u. So x has to be 2/3 of sine u. And look, now it looks like I have just pulled this out of my ass. But I did not. I set it up, which is such a classic calculus thing to do. If you ever do a course called real analysis, which doesn't involve trig substitution, it does involve a lot of setting things up after the fact, but you write it down so that it looks like you just thought of it. Okay, and so therefore, this 4 cos u squared is now 4 minus 9x squared, and so 2 cos u is root 4 minus 9x squared. Sweet. And all I have to do now is deal with the dx, because I've dealt with this bit. Okay, so we're going to go back to the beginning. 2/3 of sine u, and so dx is 2/3 of the derivative of sine, which is cos. Yes? Yes, okay. That's right, isn't it? Yep, sine has positive slope when x is 0, and cos is 1 when x is 0, so it's all good. Everything's good. All right. No, just when I'm doing integration, I get a bit mixed up as to whether it's the plus or the minus. So I just have to check for myself. Yep. Dx on du today. So you go dx on du, dx on dx, what the hell. Dx on du equals this, and then you can move the dx equals 2/3 cos u. Okay. So it's the backwards of normal substitution, right? Because in normal substitution, you go u equals something involving x, and you go du on dx. But in trig substitution, you go x equals something involving u and go dx on du. It is technically possible to set up other substitutions in this way. I've only ever seen it done like twice. And it was never an exam thing. It was always a, hey, have a look at this cool tute question. Gives us something. You have workshops, don't you? Not tutorials. Have a look at this cool workshop question that is designed to do as a group and you would never do as an exam question. So we now have all the bits that we need. And so the root 4 minus 9x squared is 2 cos u. And the dx is 2/3 of cos u du. And so now we are at this stage. And so I've got 4/3 of cos u squared du. Oh, no. This one I can do, though. I know trig identities that have squares in them. But I don't think my fundamental trig identity will help, because I can definitely transfer cos u squared into 1 minus sin u squared, but I also don't know how to integrate sin u squared. So, damn, I'm going to need a different trig identity that has cos squared in it. Okay, that's fine. Should have given myself a bit more space, but I didn't know that. So at this point, I need another trig identity with cos it's squared in it. Well, cos squared plus squared sine squared is 1. Cos squared minus sine squared is cos 2u. That's the double angle formula, one of the 3 double angle formulas for cos. And wait, it's so cool because the other ones, if I add this onto that, I will get 2 lots of cos u squared is cos 2u plus 1. The sine u squareds cancel when I add them together. So I'm going to add cos u squared plus sine u equals 1. So quite a few people just remember cos 2u is 2 cos u squared minus 1. I don't. So, and that is great because I have to integrate cos squared. I actually would much prefer to integrate 4/3 of cos squared. So I'm just going to times by 2/3. And now I can just replace the whole thing. Sweet. And so therefore my integral of root 4 minus 9x squared dx, which was at the previous step cos u squared du, is now 2/3 of cos u 2u plus 2/3 du. So did you notice I used technique 1, rewrite it. But because it was a trig function, the way of rewriting it was using a trig identity. And this I can do. The 2/3 is multiplied on, so it will still be multiplied on after I've done the integral, so that's great. And then the integral of cos is sine. But because the derivative of the inside is a constant, I can just divide by that constant. That is part of the just do it rule. It's technically substitution, but you don't need to know anything about substitution to know that that is true. So under just do it, if you would know what the derivative is when it was just cos x or cos u, and it's a multiple of that, then you can just divide by that multiple along the way. And then the integral of 2/3 times 1 is 2/3 times u. So we're doing well. We have 1/3 of sine 2u and 2/3 of u. Cool. Now, this is distressing because this one's in terms of x and this one's in terms of u. So we're going to have to put our x's back. Damn it. Okay, wait. U is trapped inside this sign here, so I'm going to have to unwrap that to figure out what u is. Okay, all right, we're just going to put our x's back. So we know that x is 2/3 of sine u, which means that 3/2 of x is sine u, which means that u is arcsine. You can call it sine inverse if you like, of 3/2 of x. Okay, so I can deal with the u. Good. Now I have to deal with the sine 2u. I do not have sine 2u written anywhere in my calculations earlier. I have sine u. Okay. Sine of 2u. Double angle formula for sine. And I know what sine of u is because I wrote that sine of u, just then, sine of u is 3/2 of x. So that is 2 times 3/2 of x. That's great. And cos of u, aha, it's half of root 4 minus 9 squared, according to this thing that I wrote earlier. Yay. Yes. And so 1/3 of sine 2u is now, they cancel, divide by the 3, half of x times 4 minus 9x squared. Sweet. And so at the final version, 4 minus 9x squared dx, that integral comes, which was at the previous step, sine of 1/3 of sine of 2u plus 2/3 of u plus c is now half of x root 4 minus 9x squared. That's what all of this became according to that, plus 2/3 of arc sine of 3/2 of x. Yay! So trig substitution, if you do the entire thing, is long. That's one of the messages. But a lot of it is looking in the working you've got and trying to find the pieces you have so that you can sub them in. The beginning, you're making working so that you can find the pieces involving x and replace them with something. And at the end, you go back to the working and try and find the pieces you've got and put the u's back, like put the x's back in. That is trig substitution. And when you look at all the working at once, you know, where'd the beginning of this question go? There. When you look at all of this working at once, which was like 2 and a bit pages, it looks really intimidating, but it can be really useful if you look at an example like this to pull apart what the different pieces were and literally draw circles around them and give them names. The first part was doing this trig identity to get the part with the root. And that all involved all of this. The next bit was dealing with the dx. And all of that allowed me to change my integral into something. And then the next part was using a trig identity to change that integral into something. And then I did the integral. And then the next bit was figuring out what all of this stuff is in terms of x, and then subbing it back in. And so that is how trig substitution works. One of the things that you do when you look at these examples is you think it is technically possible. Therefore, if David can do it, I can do it. Yes, this is true. Because I told you all of the things that I did and even made mistakes along the way and fixed them. You can do that too. And that's why I told you all my thinking, so that you could see how it was done. Now, the one thing you can't do in your exam is make all my exclamations of what the frel aloud. All my thinking I made aloud. You're just going to have to do that silently, unfortunately. Until they introduce interviews instead of exams, which is probably never going to happen, but it'd be a lovely world. Then you could tell people what your thoughts were. Yeah. But if you've ever said, if you ever have a look at any of the my own maths research, it is littered with what the fuck and why isn't this working and all the, I write those on my actual working. Yeah, so anyway, there you go. That's trig substitution. Anyone want to ask anything about any of those bits? All right. My next session starts at 1:30, but I'm squeezing it in anyway. we're going to do technique 5, which is partial fractions. And just a quick pass over it. Partial fractions is not technically an integration technique. It's an algebra technique. It's a fancy way of rewriting. And the theory of partial fractions says that if you have a proper rational function, and what that means is it's like a rational number. Like, so a rational function is a function that has a polynomial on the top and a polynomial on the bottom. Like that. That's what a rational function is. A proper rational function in a proper rational function, the degree of the numerator is lower than the degree of the denominator. The top degree is lower than the bottom degree. That is what a proper rational function is. And partial fractions is designed to rewrite proper rational functions better. That's what they're for. Okay. So that's the start. So if you see something like, you know, x squared plus 5x over x squared plus 2, that is not a proper rational function because the degree of the top is not properly smaller than the degree of the bottom. But still definitely a rational function. Whereas this that is a proper rational function. Okay. So the theory of partial fractions says that, wait, there is another theorem which is not about partial fractions, it's just about polynomials. All polynomials can be factorized into either quadratics or linear functions. It's called the fundamental theorem of arithmetic, I believe. I think. It's the fundamental theorem of something, not calculus. We've already got that one. Yeah, I can't remember what it's called. I think it's arithmetic. I could be wrong about that because the fundamental theorem of arithmetic could be that prime numbers can be numbers can be multiplied into whatever, fundamental theorem of something. That's great. We know that. So what you're going to do is that the way the theory works is it says that if you have a proper rational function, which is px divided by qx, and you know that the degree of p is less than the degree of q, and qx is factorized into linear and irreducible quadratic factors. Yep. Then oh crap. I'm just going to say with the degree of q of x is n. That's what I'm going to say. It's got degree n. So it can be factorized into linear and irreducible quadratic factors. Then there is a set of n rational functions with denominators that are powers of the factors of Q. Yep. Cool. Yep. So that, oh crap, just a second. I'm going to give them names. They should be called R1x up to Rnx. So that any proper rational function with denominator Q of x is something times R1 of x plus all the way up to, oh crap, something times Rn of x. I know this is very technical, but I just really wanted to say it aloud. So I only just thought the other day of how to say this. So this is the technical version of it. It does not sound like your version of rational of partial fractions yet, but it is there. It's saying if you factorize your denominator, then you can pull out the factors of the denominator and make them the denominators of new functions, and you should be able to make any one of these out of those functions. That's what it's saying. So just as an example, like that. This denominator has already been factorized for us. Very nice. X squared plus 1 is irreducible because its roots are plus and minus I, so you can't reduce that in the real numbers. I will make this a 2 just so that it's easier to tell apart from this one in my example. So this is degree 4 because there's an x squared here and an x squared here. So when you multiply it all together, you've got an x to the power of 4. So because this is degree 4, it must be possible to find 4 rational functions which have as their denominators things chosen from these. So that no matter what is on the top here, it can be rewritten as something times that plus something times that plus something times that plus something times that. Because it's degree 4, there will be 4 rational functions that I can use to make anything on the top if I want. So this is the first thing I wanted to tell you. The degree here tells you how many of these things there are. Because it's degree 4, you need 4 of them. If it was degree 3, then you will need 3 of them. If it's degree 2, you'll need 2 of them. If it's degree 7, you'll need 7 of them. Okay, and the denominators are always chosen from these things. The possible denominators I'm allowed to use are x plus 2, and x plus 2 squared, and x squared plus 1. That's all the denominators I'll need. I only need the powers of the factors of this thing. I could probably go up here. That doesn't even need to be all the powers, just the powers that are represented here are the ones that are needed. So here's the thing. This theorem, in fact, does not tell you what collection of denominators you should choose. Because you get to choose. I mean, you only have a small number of options to choose from. Let's be honest. But what you have to do is choose them in such a way that all 4 of these things are different. That's the important thing. They all have to be different to each other. In fact, they have to be linearly independent as vectors. I told you at the very beginning that span and subspace and all of that is reused elsewhere in your degree for things that don't look like vectors. This is one of those times. Look, it's a span. It's something times this plus something times this plus something times this plus something times this. It's just that the vectors in inverted commas that we're using are functions. But that's okay. We'll be fine. And you don't have to necessarily think about it as a span, but it's worth noting that that's what it looks like. And that's why we need 4 different ones, because the subspace of rational functions with this denominator is a 4-dimensional subspace. And so it needs 4 basis functions. It's so cool. No, no. Yeah, well, it could be. Vectors are whatever we want to use to be adding and doing scalar multiplication to today. As long as they do that in a way that works algebraically. And so, yeah, you can think of a vector, a point like an Rn vector as a function if you want. It's yeah, no. Okay, cool. You get to choose. And what we're going to choose if we're going to integrate is things we know how to integrate. You have to choose these things so you can integrate them. So here we go. Ready? I have to choose things that have these parts. That's why it's called partial fractions. I definitely know how to integrate that because 1 over x would become ln of x. And x plus 2, its derivative is 1, so I'll just divide by that derivative along the way. I can integrate that. Excellent. I know how to integrate that. That's great. I actually also know how to integrate this because, well, that's just thing to the -2, and I can put the exponent up by 1 and divide by the new exponent. That's great. I know how to integrate that. I also know how to integrate this because that's arctan of x, the integral of that. One of the things you're supposed to just know. I have run out of things that I just know how to integrate. Cursors. But that's okay. I'm just going to hope. I suppose that, I guess, these ones used up the kind of the x plus 2 squared. And I'm going to need another one. So I'm going to have x squared plus 1. If the top of that was the derivative of the bottom, then when I did substitution, the derivative would disappear and become part of the du. So I'm going to put this. Because I can put whatever I want on the top. It just has, the theorem doesn't say what the tops are, it just says what the bottoms are. So I choose to put the derivative of the bottom on the top. And then I do know how to integrate it, because if I do u equals x squared plus 1, then du will be 2x dx, and the 2x will disappear. Isn't that cool? So your lecturer will write this bit here as like cx plus d on x squared plus 1. I struggle to cope with that because it looks like I've only got 3 pieces. But if I can remember degree 4 needs 4 pieces, then this is easier for me to remember. And I know they didn't say that you can put the derivative in this spot, but they did when they asked you to do one of your Mobiuses at the very end. They asked you to adjust the coefficient so that there was a 2 there. So they did tell you that you could do that. So that's your choices. Like, you keep going until you find things you know how to differentiate. Officially, if this was squared, you'd have to integrate. Technically, if you had thing on x plus 2 squared and another x and an x squared plus 1 squared, technically, you'd need like 1, 2 times 2, 4, 5, 6, 7 pieces. That's degree 7. Oh, just give me a second. At this point, the way that you tell what A, B, and C, and D are is you put them all over a common denominator. So you multiply this one here, for example, by x squared plus 1, because that's what's missing from that denominator compared to this one. And you multiply this one by x plus 2 squared on top and bottom, because that's what's missing. Multiply this one by x plus 2 squared as well. You multiply this one by x squared plus 1 and another x plus 2. Put them all over common denominator, expand that out possibly, and compare the coefficients, and it should work. For this one, I'm not even going to do the top. You're going to need 7 pieces. So 1 over x will totally work. And you'll need a 1 over x plus 2. That definitely know how to integrate that. And a 1 over x plus 2 squared, I know how to integrate that. That's great. So I've got these 3 pieces. And then this, oh man, I can definitely do this one. I know how to do this. 1 over x squared plus 1. And we already did this one as well earlier, the 2x over x squared plus 1. That's great. We know how to do those. I've got 2 to go. I can definitely do this one. This one will be okay if I have an x squared plus 1 squared as well, because I can still use ordinary substitution for that one. Because I can call u equals that, and then the 2x will still disappear, and it's the same as this one. But there's one left. They haven't taught you how to deal with that. But I do know what it is. It's this. You'd use trig substitution. Because that's what trig substitution is for dealing with things that look like they might have come from Pythagoras' theorem when you don't have ordinary substitution derivatives to help you. You would use trig substitution. Or really cool integration by parts. Like, it's so cool. Don't even get me started on how cool that integration by parts is. But they haven't taught you how to do this integral. But they have taught you that that is the 7th piece that you need. Yep. Yeah, if it's already factorized for you like this, then you don't have to factorize it again. But if it's not already factorized, you have to factorize it. Something like that. You'd have to go, all right, is it even possible to factorize that? And so you just attempt to factorize it. Or you'd use the quadratic formula or something. And if you could factorize it, then that would be awesome. And then you'd go, that's a times something over. Something like that. Yeah. And if it doesn't factorize because of, oh, wow, I'm late. If it doesn't factorize, then you have to complete the square. Bleh. Okay, well, thank you. That will do.